Okay, I think it's time to start the session. So, hello everybody, my name is Nuutti Tervo. I'm an assistant professor from University of Oulu and coordinator of the Device and Circuit Technologies Research Area in 6G Flagship, and I'm hosting this third session, which is about physical layer advancements supporting the ITU-R technology trends. And today we have 4 excellent talks about different kind of enablers supporting these trends. There are talks about RIS stuff and talks about higher frequency communication circuits. Also talks a little bit about World Radio Conference outcome and how it has impact on the early network plans, and then a little bit more about RF circuit and RF circuit design as well. But I would say that without further jargon, I will give floor for Professor Muhammad Slim Aluni, and he will give the first talk today. Just a second. Okay, floor is yours.
Thank you, Mr. Sherman, for the nice introduction. And I would like, of course, to thank the organizer for inviting me and giving me the opportunity to present some of our work in the area of RIS. This is work led by my postdoctoral fellow, Dr. Ngoc Phuc Ly. And it's, as the title indicates it, kind of a study on the promises, let's say, of RIS-aided terahertz wireless system. And here, the key word I would like to emphasize, we are looking at hybrid active-passive RIS. This is something I will introduce as we move forward in case you are not familiar with this particular flavor of RIS. So this is the outline of the talk. I will start with an introduction, giving some background, motivation, and the system model. I will then briefly, for a general audience like this, go through the main step we use to kind of analyze the performance of such kind of systems. I will also kind of highlight an importance optimization problem that can be done given the analysis that was conducted. And then I will focus more on the obtained result based on this study. So as you know, terahertz has been a focus of many of us in the area of beyond 5G and 6G. The main advantage that it kind of promises super high terabit type of data rates in a part of the spectrum that is unexplored. But of course, you know that terahertz and generally these extreme bands suffer from a high path loss and severe blockage. In other words, they do require a line of sight. Now, to bypass the line of sight constraint, there is an interesting kind of match, or let's say, opportunity to mix or to combine terahertz with reconfigurable intelligent surface. So I think all of you know what RIS are all about. They can basically allow you to create, let's say, a virtual line of sight link to kind of bypass blockages. So if you have a blockage in the way between an access point and the desired user, you can go through this reflecting surface. And here is the first interesting kind of highlight I would like to make. You are mostly familiar, or at least when we start talking 5 years ago, or even more like in 2017-18 about RIS, we were all highlighting or focusing on the so-called passive RIS. That was kind of a main, let's say, selling point of RIS at that time. Now, 5 years after, we realize that maybe having just passive RIS is not the way to go. And the way to go is probably to go for a mix of or a hybrid version of RIS, including some passive and active. And by active is very simple, which means beyond the reflection, you will select among these reflector a subset of them that will have amplifying capabilities. And with that, you create this mixed passive active RIS. So, you know, the user scenario are many. We have talked about them in many other venues for kind of backhauling application, drone-to-drone communication, because drones tend to have their equipment facing down, so they cannot talk to each other, or same thing for car-to-car communication. As a replacement of cables, data centers are in need of, or there is a nice application for terahertz or free space optics, again, cable replacement approach in the indoor data centers. Anyway, so these are many applications that you are familiar with for RIS. And in this study, we are combining different concepts. So first of all, we are looking, as I mentioned, to passive and active RIS. So it's a hybrid form, and which means you have an RIS. Some of the reflectors are going to be assumed to be passive, and some will be active, and you'll see the benefit of that. We assume that we don't have a single RIS. We have an environment where we have a lot of blockage. So the more kind of RIS you have, the better it is, I mean, up to a certain level. So we assume that you have multiple RIS in your environments. Now, this is kind of the assumption in terms of the system model. Now, from a channel perspective, because we are adopting terahertz, one of the most popular channel model is the so-called alpha mu distribution, and that's what we are adopting in our study. And then because you operate in terahertz and the kind of hardware is not as mature as we want to be, we assume that we have some hardware impairment that will be accounted for in our performance analysis. So all in all, this is a kind of system model that we have in place. So the signal that we are receiving is basically going through this. Basically, you have L clusters. So you have L number of RIS. Each RLS has ML number of reflectors. Some of these reflectors are passive, and some of these reflectors are active. Now, for every basically transmission or every link, you have like the first hop, let's call it H1, the second hop, which is HLM. This is from cluster L and reflector M. GLM is the second hop after reflection. And then what the role of the reflector in every single RIS is to do a phase shift. And if it's active, an amplification. So if it's passive, A is equal to 1. So that's your kind of end-to-end kind of signal. So what you receive is a signal. Now, because you have an impairment, you have this kind of hardware impairment factor, phi, which is modeled as a complex Gaussian parameterized with kappa. The higher is kappa, the worse it is, obviously. And then because you have some active device, they will introduce some noise in this end-to-end communication. So this is a sum over the subset of active reflector. And then at the end, of course, you have your terminal noise. So now, given that, the end-to-end SNR can be written as function of this mathematical expression, where basically kappa is this kind of hardware imperfection factor. Gamma bar is kind of the SNR. Y is the magnitude square of this. Obviously, it's random because you have H1 and G1 random. Theta are the phase shift that you are setting up. And Z is again this random factor that is here. Now, just to make a long story short, our main contribution here is to analyze the performance of this system, which means statistically describe the distribution of gamma, so that we can derive outage probability, average bit rate, capacity, and so on. Now, because we are looking at an energy efficiency factor, we need to account for all power consumed by this end-to-end system. So we have basically transmit power divided by the energy efficiency of the power amplifier. This is the power consumed at the access point, at the transmitting access point. This is circuit power at the end user. And this is the power used in the RIS. So basically, it's a sum of the power basically added in the passive part of the RIS and the active, of course, the active part will be bigger. So this is the total amount of power used in our system. And then for the phase shifts, as you know, we can go for an optimal continuous phase adjustment, which is perfect, that we give to no error or mismatch, but this is usually hard to achieve because it's not always easy to estimate the phase in the terahertz domain. So often we go for discrete phase shift, which means you go from a continuous to a B number of bits. So if you have 2 bits, it's just 0 pi, 4 bits, you have 4 angles, and so on. So we looked at all these options. And And this is a channel model used. We use the path loss. We use the so-called PDF and CDF of the alpha mu distribution, which is a general form of many popular distribution have been adopted for all the performance analysis studies of terahertz communication. And here are the main results. So there are two kind of struggle here to analyze this, the performance of the system is to find distribution of Y and find distribution of Z, which is quite complex. You see here we have an alpha mu distribution, alpha mu added over multiple reflectors. You have this angle that can be discrete or continuous. Same thing for Z. You have basically these random variables. So to make a long story short, we use the central limit theorem to approximate both random variable Y and Z by gamma random variable. So it's like the positive version of the central limit theorem. And we find the parameter of this gamma by moment matching. And as you see, the match is perfect. So you see here in red, the empirical or simulation data, and in continuous, the basically analytical approximation based on the gamma distribution for both optimal phase and discrete phase. And we see a great match for the PDF, CDF, that's for the signal Y. For the interference Z, we see also a very nice match based on the moment matching approach that we adopted. So all in all, we have a good approximation for desired signal, a good approximation for the interference. These are gamma random variable. These are the kind of things we know how to deal with nicely. And we're able to analyze in closed form the end-to-end system. So one of the things we looked at is how does the SNR scale? So one of the main results we were able to show in the paper is that the SNR scale basically proportionally to MA and square in terms of M passive. And if you have imperfection in the basically hardware impairment, you reach a floor. You reach basically kind of a limit, which is 1 of a kappa square. So of course, if kappa is 0, it becomes infinity, which means you don't reach a floor. And there is another interesting theorem we're able to derive based on our asymptotic result, is that the gap between the optimal phase and discrete phase, in the case of no impairment, basically, it doesn't matter. Actually, you don't need to go for optimal phase because at the end, they perform the same if you have a high number of active or passive element. Now, if you have perfect, basically, hardware, no impairment, there is always a gap, as you see here, between the continuous and discrete phase. Now, okay, based on that, you can derive a closed form expression in terms of hypergeometric function for the Ausch probability. You want to get rid of the hypergeometric function, you get an asymptotic result here at a high SNR, which is kind of involving only very special functions, very simple functions. Same thing for the capacity. You can have the expression in terms of the measure function and the asymptotic expression in terms of simple function that don't involve any special function. And then once you have these results, as I mentioned earlier, as part of the introduction of this talk, you can look at the so-called overall end-to-end energy efficiency of the system, defined as basically the capacity divided by the total power. Total power, remember, is the power used at all levels from transmitter to reflector to the end users. So you can always write as I1 P0 plus I2, where I1 and I2 are constant. P0 is the kind of power you want to use to fine-tune to optimize your energy efficiency. Okay, so that was our kind of problem of interest, and as you will see, you can reach an optimum. So, you know, if you look at the paper, you can look at the parameter that we use. These are standard parameter based on terahertz, based on this kind of RIS that are used in similar papers. We assumed kind of an indoor, let's say, data center type of scenario for our study. And based on that, we looked at end-to-end performance of such kind of deployment, where we have 4 clusters of RIS, and every RIS have like here 80 reflector, here 60 reflector, and so on. So first result, Ausch probability. Obviously, when you compare here no hardware impairment to hardware impairment, of course, no hardware impairment will give you a certain advantage. And then continuous phase give you always a slightly better performance than the discrete phase. Now, analytical and basically simulation result match perfectly, the red circle and the solid curves. Asymptotic results start matching at relatively high SNR. Capacity, when you have similar to SNR, when you have basically impairment, you will reach always a plateau, basically shown here for like impairment. Without impairment, you keep growing, and there is always a slight advantage of using continuous phase compared to discrete phase. But, you know, that's kind of the main kind of result out of this. And here is the optimization I talked about. So here, what we are looking at the overall end-to-end energy efficiency as function transmit power P naught. And obviously, there is an optimal P naught that we can find based on our optimization procedure. And you see, like basically, there's always a nice sweet spot. Again, when you have no hardware impairment, you will perform better from an energy perspective than when you have hardware impairment, and continuous phase will give you also a certain advantage compared to discrete phase. Now, that's, I think, one of the main conclusion and final conclusion of this paper, which is why should we go to these hybrid systems? So here, what we are showing is your end-to-end energy efficiency as function of the number of active reflectors. And what do you notice here? If you go with 0 active reflector, which is the passive reflector we have been talking about, you know, when we start in the RIS, you get this kind of low performance. If you go full active, which is basically, you know, amplify and forward, if you will, with the relaying kind of approach pre-RIS, you get also bad performance because you start losing a lot of power in the relaying. And there is a nice sweet spot where basically you can have an active, like an optimal subset of reflector, in this case, roughly 10 for a kind of an impairment of 0.08 or maybe around 20 here to get your optimal, basically, energy efficiency. So with that, I would like to thank you, and I would like to conclude by kind of summarizing the main result of the study. Our objective was to kind of analyze the performance of hybrid, and by hybrid we mean a mix of active and passive RIS reflecting elements in a terahertz type of environment. We looked at the end-to-end performance of such kind of systems. We analyzed them in terms of asymptotic SNR, exact arch probability and asymptotic arch probability, exact capacity and approximate or asymptotic capacity. And then we kind of derived the resulting energy efficiency and the subsequent optimization that can be done to find the nice P0 to optimize the required energy efficiency. And we concluded that there is an interest in using this hybrid or mixed active and hybrid RIS because they give you a nice optimum performance from an energy efficiency perspective. And the key to all this that we were able to use from an analytical point of view, this nice usage of the center limit theorem or the positive version of it by approximating these kind of two kind of complicated random variables for desired user interference using gamma random variables. With that, I would like to thank you, and I will be happy to take some questions.
So we have plenty of time for questions, so please come there.
Thank you for that. Does the active RIS need control, connectivity for control, or is it, you know, obviously you have power supply, but do you need backhaul as well?
The active RIS, yes, will need some like control. You mean control, information control?
Yeah, of control from the network. So yeah, you essentially, presumably, you have to.
Yeah, I mean,
so
anyway,
so essentially, wherever the RIS is, maybe you could do it with power over Ethernet. But I'm like thinking from a practical point of view, when you put one of these on the ceiling or on the wall, you need power to it, but you also need connectivity to it as well.
Yes, you will need the power, and you will need, of course, connectivity to be able to control the type of element that you would like to activate or put them operating in a you know, based on the channel estimate and so on. So there will be definitely some kind of control. I think even for passive RIS, you will need that kind of control because you need to change the RIS or configure RIS based on channel state information. So I think that's a given that minimal connectivity should be for control should be made available to these RIS, active, passive, or hybrid.
Any other questions?
Fouad.
Okay, please.
Would there be difference between them?
Yes, in this model, we had some assumption. I think two key assumption. Number one, we don't assume double hops as you have seen. I assume only single hop kind of thing. And then yes, I'm neglecting or assuming that they are well positioned in a way that they are positioned to not create interference, but to try strengthen the signal in some node spots.
There.
Thank you very much for your interesting talk. Can you show me the last slide? I mean, last result. I think x-axis is a number of, yes, this one. So let me confirm my understanding. So if you would like to increase number of active parts, so then it's possible to achieving better energy efficiency. So
yes,
that is correct.
Because what happens, remember the way energy efficiency is defined is the ratio of the capacity multiplied by the bandwidth divided by the total consumed power. And part of the total consumed power, you have the power that is going to be used for the active RIS. And the more of them you have, the more power you're still consuming, and that will degrade at the end your overall energy efficiency, because the ratio, the denominator will become big compared to numerator, and the gain in capacity is not kind of compensated by a kind of an increase or a similar increase in the increase in power consumption is not compensated by similar increase in capacity.
But does it mean like if we use all of ROS as the active one, it's possible to achieving the best energy efficiency?
Yes.
Or is there any, okay.
Yeah, so this is exactly what I was saying. As I'm saying, there's a nice sweet spot in the number of subset of elements that you need to kind of activate in order to maximize your energy efficiency. I mean, the more you activate, you have higher capacity, but this is going to come at the expense of higher power consumption.
But how about the actual capacity for this part? I mean,
oh, okay. I don't have a slide on that, but clearly capacity is going to increase. The more the better, because you pump a little bit more power. But again, the rate of increase is not interesting enough to compensate for the amount of power that is going to be used, and that's why you are using this energy efficiency metric to capture this trade-off.
Okay, thank you very much.
Okay, I think we can take one more and then move on.
Thank you. So yeah, actually to add on the question regarding the performances. So this was conducted in the terahertz spectrum, right? Have you done any similar assessment in the 5G spectrum?
In which spectrum?
3.5 gigahertz and millimeter.
No, that would be not interesting. I mean, obviously the methodology will be the same, but the channel model will be different. We may not consider channel impairment. So, I mean, we can develop the same mechanism or analytical methodology, but the analysis will be different. The channel model will be different. The channel hardware impairment will be different. Parameter will be different. So it has to be different study.
Yeah, I'm saying that because it's already deployed in a 3.5 gigahertz. If you go to Thailand, ZTE actually, is already commercializing RIS. So then think about China. So, the next question is, are we behind here?
Are we behind?
Yeah.
In what sense?
Well, I mean, do we need to catch up here in Europe?
Oh, you mean in terms of RIS?
Yeah.
Oh, yeah. I mean, that's a very good debate. I mean, that's why we are on the 6G summit here, is to push the technology that hopefully will make it as part of 6G.
Yeah, because I see it, in the 6G bucket, but it's already there in 5G. So I guess,
yeah, but I mean, I mean, there are different flavor of RIS, right?
Yeah.
I mean, like these RIS
Absolutely,
terahertz
yeah.
is, so, I mean, you can always improve. I mean, a simple reflector can be viewed as like a first generation of RIS. So I think you can put very basic RIS and you can make it more sophisticated by accounting for this multi-surface, this multi-functionality. So this is ongoing studies. Now, is it going to be adopted as part of 6G in Europe, in US, in China? This is beyond my level. But I believe there is hopefully room for some RIS to be deployed in some of these kind of new the markets,
Thank you very much.
I think it's time to move on. Thank you, Slim, for a nice talk. And we move now forward to a little bit, let's say, other end of this kind of a research. So we go and discuss about circuits and heterogeneous integration. And Giovanni from IMEC will give a nice talk about that.
Thank you, Nuti.
So just a moment.
Yes, in the meanwhile, I say I am very happy of being here. Good afternoon, everybody, and also to the people online.
Okay, the floor is yours.
Thank you, Nuti. So I come from IMEC. It's a research institute on nanoelectronics. We investigate many things from material technology to biomedical, yeah, so many things. In this context, I give a brief point of view on heterogeneous technologies towards a sustainable and efficient 6G. We know from this symposium that each of these words can have a broad meaning. So I will explain my focus. First of all, I focus here on a millimeter wave, in particular, moving above 100 gigahertz. But many of the considerations that I express here are valid also for lower frequency. And I wish to shape my talk according to these three points of view. I call demand pool for a 6G efficient millimeter wave. Then there is a heterogeneous technology push. Here in my talk for technology, I mean the material technology, silicon versus indium phosphide, gallium nitride. So with technology, I mean material technology. And the third point that it's good that gains more and more attention, sustainability. In my talk, I focus on sustainability of production of the chips. If we talk about sustainability of operation, during operation, I consider it as energy efficiency. And then I place it in the demand pool for an efficient millimeter wave. I give the point of view from IMEC. For a millimeter wave radio at IMEC, we are actively investigating from semiconductor to circuits and applications to antenna packaging and systems and algorithms. So higher frequencies allow for extreme high data rates and extreme fine resolution. Data rates are interesting for communication. And the resolution is interesting for sensing and localization. So this is interesting where we wish to combine sensing and communication. Here, I report some frequencies from left to right going higher in frequency. There is the 5G FR1, the 5G FR2, and then candidates, let's say other parts of the spectrum. And we see from left to right going higher with frequency. We have also that the typical bandwidth goes higher. And we know this means a higher data rate. And below, looking at the physical properties of the wavelength, we see that we can reach a fine resolution for sensing in terms of range, angular resolution, and speed. On the other hand, with the frequency going higher and higher, so millimeters, let's say, then the packaging becomes challenging. If we consider a phased array system, in this case depicted on the left is a transmitter, And we know that for an optimal electromagnetic use, let's say the antennas needs to be at a distance of lambda over 2, the wavelength over 2. From a study reported on the right, higher frequency, lower lambda, the array size goes down and then becomes comparable even lower than the chip size. The chip size, in first approximation, the size has to do with the functionality that we want to put on chip. So there can be this conflict here. Now, going to the circuits, from baseband to antenna, if we go from the right to the left, so from baseband to antenna, we can classify mainly 3 families of functionality, let's say. And here I am simplifying a lot. In this context, I'm simplifying a lot, so I give just a simplified perspective. We have here the digital modem that has the digital signal processing, and we can consider here also the conversion from digital to analog or analog to digital. Then we have here the RF functionality, RF chip, that has the frequency conversion, up conversion or down conversion, and the frequency synthesis to synthesize a clean sampling reference signal. And then we have the front end close to the antenna, where here I place a power amplifier for transmitter or a low noise amplifier for the receiver. Well, ideally, for each of these families of functionality, we would like to choose the optimal material technology. So for the digital modem, we go for silicon, for CMOS. It's best at power, performance, area, and cost of digital, fast digital operation. For the RF chip and the front end, since here the functionality is more on analog RF, there are other figures of merits. It's not as the fast digital operation. We have, for instance, a need of a high signal-to-noise ratio. Also, we have analog operation at high frequency, and also we have parasitic effects that impact the performance at RF. Now, for this functionality of RF chip that is in the middle, we still have nowadays a lot of digital functionality needed also for this RF chip. That's why for the RF chip, we still like silicon for a fast digital. We would like an improved silicon, a silicon that also has capabilities for RF, especially for beyond 100 gigahertz. In this case, a good candidate is the so-called SOI, silicon on insulator. On the left, for the RF front end, we actually can benefit from other materials. In particular, for above 100 gigahertz, indium in the compound of indium phosphide shows a good performance and efficiency for above 100 gigahertz. So now, if we consider a case of a transmitter phased array, and we say, okay, the RF chip is in CMOS, SOI possibly, and the power amplifier, which technology? So we have this case and we fix, for a fair comparison, let's say we fix the equivalent isotropic radiated power that we want. So in this study that we performed at IMEC, we compare the power amplifier in CMOS in a silicon germanium and indium phosphide. And we vary the number of antennas and we estimate the power consumption of the transmitter. Now here we see that using indium phosphide instead of CMOS, of silicon, we can lower power consumption, and also we lower the optimal number of antennas. So it means that we have lower power consumption and smaller footprint. On the other hand, this requires a more mature and cost-efficient indium phosphide technology. Here, silicon is very mature, silicon and cost-efficient. Indium phosphide a bit less, and also requires integration with CMOS because we still use a CMOS for the other functionalities. Here comes what in my talk I define heterogeneous technology push. We have different technologies for different functionalities and put all together. We have, in this case, indium phosphide for the power amplifier, for power and efficiency. We have CMOS, possibly SOI for the RF chip, functionalities of beamforming, calibration, and control. We have an advanced packaging and heterogeneous integration that allows to integrate all these things tight, close to each other. Again, I emphasize on the tight because going higher in frequencies, the lambda gets smaller and we need to be compact for this system. And also we have the antenna array directly drawn, directly embedded into the packaging. So now there are different possibilities for heterogeneous integration. Here, I just report 3 on the right of this slide, things that we have been investigating at IMEC. The first one on top is a 2.5D. We see here CMOS. In this case, it was for lower frequency. Gallium nitride can be indium phosphide for high frequency, that are flip-chipped and mounted on an RF interposer, and then also another package here. The solution in the middle, the chips, 3.5 chip and CMOS, are inside the RF interposer. Let me rephrase, the RF interposer is grown, is fabricated around these chips, the CMOS, the silicon, and the indium phosphide or gallium nitride chip. The solution on the bottom is even more intriguing. At IMEC, in our fabs, in our clean rooms, we investigate. We grow the 3.5 device, for instance, indium phosphide, directly on the silicon wafer. And ideally, we could also then do a patch antenna in the back end of line if we go further. I give you an example for here. For the solution in the middle, actually, I'm happy that I heard already that we have heard about European effort and CHIPS joint undertaking. This is a project on which, okay, I am working, IMEC is working, SHIFT, and there are different partners here. In particular, here there is the task for a future G transceiver. It's a 140 gigahertz transceiver link. Here, the core of this project is the heterogeneous integration. We have on the left the transmitter, on the right the receiver. And if we focus here on the transmitter on the left here, we see in green the RF chip in BiCMOS from ST Microelectronics. And on here we see the power amplifier in indium phosphide from a 3.5 lab in France. So these two chips of different material technologies are going to be embedded within the same advanced RF interposer from AT&S. This heterogeneous technology integration on PowerPoint is very easy. Of course, you can imagine that there may be many challenges, even just the electrical contact from the silicon chip or indium phosphide and the interconnection. Already that is already a challenge. So now I go back to indium phosphide, and I show here some possibilities of getting these indium phosphide chips devices. The first one here on the left is the one currently available commercially from foundries. There are foundries that make wafer, and then from this wafer they dice the power amplifiers, the system in indium phosphide. Another possibility to integrate indium phosphide onto silicon is to dice here the devices, and then to, let's say, I say easily, bonding these indium phosphide devices onto the silicon wafer. This other solution, intriguing, that we investigate at IMEC is to directly grow indium phosphide on top of the silicon wafer. This is based on heteroepitaxial growth, and we see nanoridges. Here there is a beautiful, or I mean, for me, beautiful, I mean, as a technologist, I mean, a beautiful cross-section of the nanoridge in indium phosphide grown epitaxially over silicon substrate, silicon, yeah, front end of line. I've been talking about the demand pool of mmWave technology push. It's beautiful. What about sustainability? So in this context, I just give a brief mention of sustainability in the production. We have seen in this forum that sustainability has a broader view. I give here just a consideration on the production. If we consider a user equipment, for instance, a smartphone, we see that actually from this study, 70% of the carbon footprint comes actually from production. Then only 20%, at least according to this study, comes from the use of the smartphone. And from this 70% of production footprint, half of it comes from the fabrication of these integrated circuits. So actually the fabs have a lot of footprint here. So at Timec, we engage in a life cycle, or we start to engage in a life cycle assessment defined according to some standards. So we consider, or I mean, we start to consider the mining materials, fabrication, use, and end of life. I say we start to consider because this study in these years is evolving and evolving. For instance, here we also don't consider geopolitical tensions or also sustainability, such as the mining, how the people, how to say, in which life condition they work to do mining. Now it's purely on the energy consumption for the moment, let's say. Indeed, so in this case, the considered indicators are water consumption in the fab, especially, and the global warming potential. Here, I'm just mentioning, I'm not giving details, but let's say in this study, there are 3 processes under consideration. So here on the left, there is the current commercial fabrication of indium phosphide substrates, 4-inch. On the right, here we have the available silicon wafer, 12 inches. The reference process here is a 28 nanometer CMOS. And in the middle, our this investigated process at Timec of directly growing indium phosphide on the silicon wafer. So here, to summarize, what we have seen in this study is that this novel approach that we propose at Timec has a global warm impact of 30% higher with respect to the reference technology, silicon technology. On the other hand, remember, I told you some RF performance is not efficient at silicon. But yeah, still we need to consider that this process would require, I mean, it's 30% higher impact than the reference. If we go to the process on the left, still the model needs to be better refined. We had still a lot of variation in our estimation because the indium phosphide fabrication itself is not as broadly spread and known as silicon, let's say. So we need further work on it. Further details on this sustainability study of chip fabrication is available on the imec.net zero platform, accessible for partners, of course, but also for a public user, imec.net zero. With this, I come to conclusion. So here I say we have a demand pool with the mmWave frequencies, especially above 100 gigahertz. We have a promising data rate and sensing. On the other hand, the higher frequency means smaller lambda, and this poses challenges on the packaging. From circuit point of view, from baseband to antenna, we have different families of functionalities, and we would like to optimally choose the material technology for the digital modem or for the RF operation. With heterogeneous technology, we can integrate multiple chips into one RF interposer, into one RF system. Or at Timec, we are investigating to directly grow this indium phosphide technology or gallium nitride, I have not mentioned this here in this talk, directly onto the silicon front end of line. And about sustainability, we need to remember that, or I mean, in this talk, at least I give the point of view that the production has a big impact. So at TIMEC, we engage or start engaging in the life cycle assessment. And with this, I wish to thank my colleagues at TIMEC and the Free University of Brussels, and to acknowledge the CHIPS joint undertaking and the European effort. Thank you.
We have time for a few questions. Okay, let me start from there.
I have a question regarding the packaging. How do you see the packaging with interposer and the wafer level packaging? How do you compare? How far we are from wafer level integration of 3, 5 and silicon? So is IMEC doing any circuit design in that particular packaging, or how do you compare these two technologies?
Yes, thank you. So for the packaging, so you're asking a comparison of the different packaging, in particular the one with the different chips into one RF interposer, and the other solution that I say we integrate directly. So this last one is a medium long term. Okay. I mean, for that one, there are, the integration itself has been proven at TIMEC, but of course, to make it mature and robust for then a product still is far. So the one that I see closer is so taking the chips from different fabs, so the silicon chip, so actually the European project that I show, I think this is closer to industrial, okay, not yet robust for product, but it's close, because actually different partners there are involved in different steps. Actually, this is a good point because it shows the level of almost industrial or production maturity. So I would say at the moment, as far as I know, also from some industries, companies, that's the one they are looking at. So different chips, the digital modem, RF chip, and the front-end chips with different technology. And actually more mature is maybe the one that I showed first, and I didn't talk much. Actually, these chips chipped on top of an RF interposer. So actually, that's even more mature. There are already solutions with that. So yeah, the more mature is from the top that I showed till bottom. Okay. But the one in the middle is getting relatively mature. The one on the bottom is for the medium long term.
Okay, in order to keep the timing, I suggest that we give applause for Giovanni and move for the next talk. So thank you.
Thank you.
Thank you.
Yes. So next we jump from the higher frequencies a bit lower and talk about a bit industrial perspectives on these kind of aspects. So Reikki Näslahti from Nokia, floor is yours.
Thank you. Thank you for the great presentations earlier. And I think the point was made very clearly that there will be huge capacity need for 6G. Especially when we discussed the use cases. I was astonished with the numbers you said. And then if we look at the picture like this, so the frequencies versus the capacity of the traffic. So if we first look at the green part here, which is the regular mobile traffic, well, that keeps on increasing. But now there is more and more fixed wireless access. 5G almost like afterthought for many, gave the big use case for 5G, the fixed wireless access, and it's being built globally in many places. That traffic on top is a heavy one. And then, as discussed earlier here by many, XR, so the AR and VR on top for both mobile and fixed wireless access. And we have even more traffic. So this is the global traffic growth. And if we then try to understand how a typical average operator can handle all that. So let's say 4G frequencies, all different FDD bands, 80 megahertz worth of frequency assets altogether for an average operator. And already a few years ago, we started to see this phenomena that it's simply running out. You needed more capacity. Thankfully, the 5G came. Typical case again, giving 100 megahertz new frequencies on 3.5, 2.3, 2.6 gigahertz bands. Big addition. And with that one, we can go quite far. In this example, we would see somewhere there 28, this capacity running out. But luckily again, the 6G comes 29, and here, let's say, typical operator would be getting 400 megahertz worth of new frequency. And then we jump from something like 7 to 75 zettabyte per year type of capacity. So timely addition of capacity with 6G. How many of you were in a World Radio Conference in Dubai end of last year? Anyone here? At least a few. So thank you. I was expecting a lot worse outcome than this one. So good work, thank you. So we got good layers to the cake. We got even the upper 6 gigahertz for many countries as a potential 6G band from 6.4 to 7.1. And then I would say the most global band for 6G, the 7.1 to 8.4 gigahertz, plus some around 14, 15 gigahertz, 4.4, 4.8, and even something below 1 gig. Plus, coming back to the previous presentation, the sub-terahertz above 90 gigahertz. Plenty. Thank you. But there, I mean, it's not that trivial. If you look at then this split in a global scale, poor colleagues, friends in US, as a 3GPP guy, I would say that you did the mistake and you gave the upper 6 gigahertz to unlicensed. Same thing in Saudi Arabia. But okay, even there we can do something. I mean, we have done it before. We have put 4G on unlicensed band. We have standard for it for 5G. We could do the same for the 6G. Why not? Plus then the good thing in US is the whole 7.1 to 8.4 being there. There we have a problem in Europe. In the middle, we have a NATO using the frequencies on this band. Many countries, many regions, we can indeed take the right decision for the upper 6 gigahertz and make it licensed IMT band. Many countries, regions, we have this 4.4 to 4.8, good 400 megahertz worth of frequency in a good frequency range. Plus then the higher frequency, which is getting more towards the millimeter wave of building the products. But especially these around 7 gigahertz frequency bands, how do we build the networks there? How do we make it commercially viable for us, vendors, operators, for the whole ecosystem? We need to do something like this. So we have learned it the hard way as an industry, the gravity of the site grid. So when we, for instance, in the early days of 5G, in some places we were forced to start the 5G with millimeter wave, which you really cannot deploy from the current sites. We were very creative building the new sites at the lampposts and traffic light poles, covering the city canyons, soon going indoors. It was difficult to get the richness of the end user devices, the UE supporting millimeter wave as well. But really this gravity of the site grid, it was so difficult. So in US, we needed to start with the mmWave. But as soon as the C-band, the 3.5 gig came available, boom, it was a nice 5G introduction there as well. Plus for the others who started with the 3.5 gig. And it really is how the networks are built. So it needs to be, this box needs to be roughly 40 to 70 centimeters and less than 20 kilos. And then it's deployable to the current site grid, to the current site infrastructure. A person can carry it. You don't need a crane to install it. So that's where the kind of simple limitations come from. And we cannot get around it. Good thing now going to a little bit higher frequency is that, well, we can pack more into the box. Same size of a box, we can get, for instance, the antenna elements, we can put 4 times more or even more. But so some kind of typical today's equipment we have as a massive MIMO product, the 64 TRX product with 192 antenna element. We can go to 768 antenna element in the same size of a box. This will, of course, improve the uplink performance. It will also help us to put more TRXs for the same size of a box for the capacity. I think good target for the, if you think it, the system perspective as a spectral efficiency is, let's make it 20 times better than 5G. So if we go from the typical 5G 100 megahertz to 400 megahertz, multiplier 4, and then the multiplier 5 coming from more TRXs, AI based air interface, better receiver algorithms with the AI and all that. 4 times 5, 20 times spectral efficiency. I think that's a good target for 6G versus 5G. Now talking about the centimeter wave. And we started the journey, we wanted to test early. So this is something, so basically doubling the frequency from 3.5 to 7 gig, having more antenna elements, having more TRXs, doing a massive MIMO of that kind, comparing it with the typical today's 64 TRX product. And the first measurements show that in terms of the link budget, in terms of the coverage, it's pretty okay. As I discussed with some of you, yeah, it's more difficult to go through the walls with the double frequency. But at least when we first look at it outdoors, it's doable to deploy it from the current site grid. We still need to work on the indoor a lot more. But then there is other topic I've been discussing with many of you. I mean, we need to respect the fact that there is, again, something else on these frequencies. Even though we got the good result from the World Radio Conference, yeah, there are other stuff like the geostationary satellites, for instance, picking one example here. This is the challenge we are facing in many places. So if we then first think about the uplink of the satellite, so let's build a solution where we are radiating below the horizon only. Let's work out the side lobes of the new massive MIMO 6G product so that we are not interfering the satellite system. And then on the other direction, the downlink, when we are close to these Earth stations, some kind of filtering or spectrum sharing, dynamic spectrum sharing is needed. Some of these frequencies will be cleaned up, but let's be prepared for the fact that not everything will be. So to summarize, there is going to be a huge traffic increase. We need to cater for it. 6G comes, good timing. We get these new frequencies. let's make sure that we carve out like 400 megahertz for average operator globally of these good around 7 gigahertz centimeter wave bands. And then we need to build the product so that we can build them on the current side grid, which is the gravity. And then we need to also solve the coexistence with the current systems. Thank you.
Okay, thank you very much for good talk. So we have plenty of time for questions, and let's start from there. Okay, so from there, who has the mic now?
Thank you for that. Let me respond to your unfortunate decision by the US to make upper 6 gigahertz unlicensed. As we discussed, I mean, the upper 6 gigahertz in the US is got a huge number of incumbents, mostly fixed links, many critical services, public utilities. So if we had gone IMT, we would still be looking at that spectrum. Meanwhile, right now in the US, you have a huge deployment of unlicensed already happening using Wi-Fi 6E. University of Michigan has 16,000 Wi-Fi access points operating in that band. So the band is being used very well to serve indoors. But I would encourage you to get 5G NRU out there. I do think that the IMT folks are missing out on an opportunity of accessing 1.2 gigahertz of spectrum, which can be very easily aggregated, just like LAA was aggregated in 4G. And I'd like to hear a little bit as to why that opportunity, why that is not seen more as an opportunity by 3GPP or IMT for harnessing that huge swathe of frequencies using 5G NRU.
Yeah, thanks for that one. I mean, maybe we start from the 4G learning. I guess we, as an industry, burned our fingers a bit. We tried to make the LTE unlicensed happen, and we got some distance, but not the whole distance. Not the kind of commercial success with that one. And I have been talking with many of the industry kind of partners of ours on this one. So talking also the chipset vendors, the device vendors, and there seems not to be appetite for it. For a network side, it would be quite trivial for us, basically yet another frequency variant, and then doing the listen before talk features, which we have already developed. So it would be quite straightforward for us. So we would like to do it, but haven't got the rest of the industry, especially the device side, with us. So there is no appetite. But now looking at this picture, I'm pretty sure that there will be.
Okay, gentleman there.
Yeah, thanks. Joseph Noll, University of Oslo. From my former background of head of passive remote sensing at the European Space Agency, I'd love to ask you whether you want to make yourself enemies or friends, because 6.8 gigahertz is the key passive remote sensing frequency for sea surface temperature. And doesn't matter what you do, you never reach the required minus 170 dBm for passive remote sensing if you have any activity somewhere close to that.
Yeah, thanks for the question. I don't want enemies, but this is yet another challenge. So thank you for reminding us. Let's go backwards. Always, I mean, we started GSM on 900, and then somehow we managed to get to 1800 in use, and ever since there has been new frequency taking to IMT, and there was always something on that band we were able to take to IMT use. So in that sense, nothing changes. Did we make enemies in the past? I guess sometimes we did, but let's try to make it more as friends. let's try to coexist in a best possible way. But there is always something we need to sort it out.
Okay, there's one more question. The guy who had the mic previously, could you please pass it back there? So he was the next in the line, and this is the last question we can have, and then we have to move on to the next one.
Thanks. Given that the mobile industry is always talking, including today at the European Ministers' meeting on telecoms and infrastructure investment, is always talking about the challenges of growing traffic against slower growing revenues. Is it wise to seek to expand FWA, given it uses 20 to 30 times more data traffic per user than mobile broadband? Yeah, aren't we essentially saying, actually, we'd like to create more of this problem with exponentially more traffic through our own choices rather than doing mobile as a mobile industry?
Excellent question. So if you would ask somebody like T-Mobile US, they would say, yes, of course. They have created several more billion dollar extra business with it. Same thing if you would ask it from Reliance Jio in India, yes. So it's when there is enough capacity and you realize that the mobile broadband is not consuming all of it, what do? Let's do fixed wireless access. But you're absolutely right. You get more dollars per hertz in the mobile broadband, so you need to be careful that you don't make that system suffer. So you need to do a slice or some kind of a solution so that you always secure the kind of part of the network, the part of the traffic, which gives more euros or dollars per hertz than the fixed wireless access. But because there is the excess capacity, why not to use it?
Okay, thank you very much for a good discussion. I think we will move on in the agenda. So thank you, Ari. And so next talk is by Professor Arno Pärssinen from University of Oulu, and we dive in back to these circuits again for the next 20 minutes. So Arno, floor is yours.
Thank you very much. And indeed, today I wish to go a bit deeper in the microelectronics and some of the things that are of importance when we are designing 6G and why we need to understand this field deep and thoroughly. So I ask the same thing as with Ari. So who has ever designed an IC circuit? Bit less than I wished, but still someone. Anyways, this is kind of an obvious. So we have the enablers and we go with those. We need to have the enablers well in advance compared to what we are trying to do the products. That's why some of these interests, what we are discussing today, might not be 6G. They were potentially to become 5G. We know that the market has not ramped up. It doesn't say that there wouldn't be any easy solutions for the lower frequencies either. But we need to master the technology. We need to understand the technology to be able to use it. One of the things in microelectronics is very difficult for many of us because it's actually a very, let's say, highly multidisciplinary field in itself. It's complex. It requires a long education by itself. People who are interested to that are more interested about the physics than mathematics. And we are kind of having then three different kind of elements. And it's very easy to look at it from the software system product design perspective. You need to make the products, you integrate the products. If you want to be really competent and capable, then you go at least to the next level, which is the fabless chip design. Because if you are mastering the integration and system, you are having the opportunity really to understand where the power is consumed, what is happening for your algorithms, what is the interference that you need to be protecting against. So you make friends if you know how to avoid some of these highly physical things that are called sometimes RF, sometimes spectrum. And it's us who are either doing something good or destroying the whole behavior. And then we are having the semiconductor manufacturing and fabs. And we used to have that all in the same package. And that's been gone already for a long, long time. So I've been always a fabless chip designer and going from to the system side. But if we then look at the portfolio and how companies are working, we're having still a few real fabs, TSMC, Global Foundries. Then we are having a lot of companies that nowadays have become higher and higher layers. And then we are having companies like Apple, Nokia, Ericsson, who are designing part of their system in a fabless mode on their own. But very few of them are having the whole kind of ecosystem in their hands. Basically, Samsung could do it. But also their mode, to my understanding, is more like that they are doing fabless chip design. They can pick from anybody to their products the wireless solutions. So if the in-house is not good enough, they can do something else. So it's layered even between the companies. This was, of course, speculation, but that's how I'm understanding it. But they also understand what is happening in the fabs. And they've done pretty well in their business as well. Then we are having the classical model for the wireless chipset has been indeed in the fabless mode. Qualcomm, MediaTek, so forth, Broadcom, Nordic Semiconductors, and a lot of that. Also in the digital side, we are having NVIDIA, AMD. They are definitely doing very poor at the moment if I'm looking at their stock market. So that's not a bad model. They are understanding the system. They can go for up and down. But we need to be very careful what we are doing with the fabs. And this is the idea from Kevin Chang from TSMC, how this system is indeed kind of developed. So TSMC found this model of that they are changing the foundry and fabless compared to the original one that was IDM. And integrated device manufacturers have changed this model gradually, many of them, to be either fabless, either foundry, or kind of having a mix and match on those wisely. And this is important aspect because myself as a designer, I've been designing wireless from also in the industry from that point of view that I had a system understanding and I needed to move it to the circuits. What is the best optimized? And that's a very nice position because you hear from your own company details. You can be a bit more advanced. We can prepare beforehand. And then you know the details, tricks, and so forth. And if you, then it's possible also in standardization phase to optimize the system much better. So making it more energy efficient, making it more sustainable when you're knowing what is really happening. You know the finest details. In HexaX, we were really building the first phase in the right momentum. So looking at also enabling hardware technologies, not just radio channels, MIMO, waveform modulation, beamforming, but really wanted to bring already the early view on what hardware could be, what are the real limitations, and especially when at that time 100 to 300 gigahertz was a very hot topic. I know some of my colleagues in the communication side were asking from me that why not you are doing 1 terahertz? Sounds a bit naive nowadays, but that was kind of the bad thing that I was promising only 300 gigahertz. So it's a bit different than what Ari is now dreaming about. But I would say that as an RF designer, you should never go higher than you really need. That's rule number 1. But when you really need it, then you need to go high. And then you need to understand what you need to do in the high frequencies. For me, transistor is the device, and wireless system is like a radio link. So keep also updated with the terminology. Then do we have a use case for the terabit per second? And this is friends from Keysight who calculated this one. And if you really want to go high end in holographic communication, you would like to have a whole person size view having 60 frames per second and have all of that. It takes 4.3 terabit per second. So everyone who is working with the holographic communications, maybe you can compress it a bit, but your friend there, that's 8 terabit per second, and all of us with the same resolution, that's going to be quite many hundreds of terabits per second. So we really need to understand also how we are scaling these things up and down. So some of the dreams, actually, what we are listening here, are requiring actually substantial amounts of data rates. At the same time, we need to be sustainable, reducing energy consumption and so forth. So there is often a dilemma. And that's why make sure that what you are dreaming and what you are promising is also feasible. That's why you need also the hardware. We are consuming the power. MATLAB is not. AI is consuming the power, but it might be consuming it somewhere else, far away, as many services in the internet and in the cloud. So you're just changing the trouble to somebody else. But the sustainability aspect is there. As we go higher in the frequencies, we are getting poorer transistors. We are getting lower output power. We are getting higher noise figure and so forth. So we start all of that. And part of this negative things, what are happening actually in the millimeter wave and terahertz side, are coming from that, because you don't have the same hardware. You are having a bit worse hardware. You need to increase the number of antennas more than actually the antenna aperture would require. On the other hand, you are having the beamforming, which is nicely compensating for that. So there are actually 3 aspects you need to take into account very carefully in the implementation. Then I would like to talk about a bit what it means and what it makes. And I have here now the mountains of radio hardware and RFIC design. And let's look at a bit of a history. And there are always 3 decades in each of these frequency bands. The first one is feasibility. The second one is large-scale integration. And the third one is maturity and advances. And if we think about the 1 to 2 gigahertz range, it was in the 90s when we did the feasibility. We were able to do in 2000 single chip GSM phones. Everything that was said when I was studying that you cannot integrate power amplifiers, you cannot do that and that and that happened actually in 10, 15 years from the day one, what was said to me to be impossible. And all of those are being used right now in different products. In 2010s, it became kind of a very challenging for academia from that perspective, that the solutions were extremely complex. They were extremely optimized. You needed to have a very, very high-skilled group of people of doing it. Academia is not doing the highest complexity microprocessors. It's impossible. And the same happened for the wireless as well. We cannot compete with the industry with the complexity. Lower millimeter wave side, it was ramping up with the 60 gigahertz research, and I was at the company at that time and really was saying that we will never need it. Never was, once again, I should never say never. We will need it, but for the short time I was right. But people in the academia were doing the feasibility. They were working with the topic. 2010, it was kind of mature enough for the large-scale integration, and then advances 2020s. So we are basically having there a lot of technology elements ready to make real products that are as optimal as they can be in that domain. with the higher sub-terahertz, so we are going above 100 gigahertz and we are working up to 300 gigahertz, we are still in kind of the fact that, yeah, we start to be that we try to make large-scale integration with the different technologies. But there is, if you can see in the picture, there is the flat plateau. Getting there, we are having a major danger now. There you see the slope going down. If we give up, we end up to the valley with the things that we have invested a lot. And then we are not anymore ready to go to the plateau in 10 years from now when you're going to need it. So something that, where you need to have a very, very long-term perspective. We see it now in the European Chip Act, as we discussed yesterday, 10, 20 years kind of giving up, now need to take back. That's why I see there is a role, at least in the research and in a specific product development, to take also higher frequencies forward and not just give up, because they are still a bit too difficult for the industry that is in the mainstream. Let's try to keep a balance in that. And then I wanted to show a bit what we have done. And this is, students can do 8-channel, 28 gigahertz millimeter wave transceiver with the new architectural aspects and so forth. And transistors you cannot see anymore. You can hardly see inductors and so forth. This is like 35 square millimeters large chip. And those who have designed ICs know that it's pretty much impossible for the 5 guys to make the chip design, but these guys did. I appreciate their work a lot. And that was, as Jerome was saying, it was CMOS SOI. As we went higher, my philosophy was that if you can do with a silicon, you should do it. That's why I didn't take the 3 to 5 into use, but we used the best possible silicon germanium process. And we did quite some circuits, and you see small circuits. You start to see even transistors there. You see much more because we are kind of looking at the feasibility. My first student is now indeed close to finalize his PhD on that topic. And we discussed in the beginning that this is supposed to be impossible. But he showed also that this is possible. That's why he is graduating. And we can move on with that to the next phase. Interesting thing in this scaling up in the frequencies is indeed that what kind of environment we are going to have. And that's changing drastically because we know that at 3 gigahertz, the antenna is large. We can kind of get the same antenna aperture having a phased array. That's the reason for it. But it's getting small. And then this tiny part of there is my small antenna at 300 gigahertz, the same basically antenna element, just scale over the frequency. What happens with my electronics? So the first one is a commercial chip for the base stations made by Analog Devices, published. It's just 2 channels for the 1 antenna, very nicely compact. You see that it's tiny compared to the antenna. In 28 gigahertz, we can do roughly these 2 times 4 channels in the area of 4 antennas. So, and if they are dual polarized, that's happening very nicely. As we are going to 300 gigahertz, my antenna is the same size as my LNA, where I put my rest of my transceiver. So my electronics start to get big. So we are having different kind of challenges now to integrate everything that we need to learn. And we are also working at the frequencies that are 2/3 of the Fmax. I would like to have a bit faster process to make it nicer, but it's never going to be the same as when I'm designing at 1 to 2 gigahertz. And that's why I cannot expect the same performance. And this is actually the same picture as Giovanni was showing, and this was done with the IMEC, actually, with Piet van Bak when we were doing the first white paper on this, and this was really the IMEC's vision at that time already several years ago, and now we saw a bit more details. So use the technology that is best for each area, and then do the heterogeneous integration with that. And I'm happy to see the progress in that area. The other important part is that in digital side, people have noticed that this is actually the cheaper way of doing it. So they would like to do smaller chips, integrate them heterogeneous way, and they have calculated they save the cost. That's quite a drastic change because every time before this, everybody has said that the cheapest way of doing it is to integrate as big chips as possible. Even that, which is forever, has changed. performance. This is indeed interesting. I compared several technologies, and there is silicon germanium, and that's relative range. And I think that the operators like this one because this is giving directly the difference between what is the technology difference, so forth. So I calculated link performance and relative range. If I'm having a silicon germanium 28 gigahertz solution with the same antenna size, antenna aperture size, I get 9 times more range compared to what I'm getting at the 200 gigahertz. And even if I'm putting the indium phosphide there, which is a better technology, I'm still lower than at 28 gigahertz. So this is a kind of a sign. Never go to the frequency if you don't need it. It's not economical also from the technological point of view, but sometimes we need it. It was very interesting to see the photograph of the black hole. That was done at 200, 300 gigahertz range with the radio, not with the normal photography. That's why we got it out. So there is a use, and maybe we get these holographic things happening, and that's what is make. So what, when, how? Technology will never take us automatically forward. Even more slow anymore because you need to have a heterogeneous integration on the digital side to optimize your cost and your user happiness. This is always a multidisciplinary thing. Even within our own domain, this is multidisciplinary. I cannot design a transistor. I'm just a user for that. And I need a lot of friends there. Then I would like to convince my friends in wireless side that, yeah, please come and discuss and let's try to find something that we can even talk, that this goes right. Therefore, hardware aware or even hardware friendly protocol design for the 6G, I would say it's a must, whatever frequency you are taking. New use cases will come after enablement. So it's a bit difficult to think about them in advance, what is really happening. If we are thinking them too far, we are going to have a very much a disappointment in our marketing because technology was not there yet. So let's keep the customers satisfied and also test our dreams in advance with some real thing, which is also economically and power consumption-wise satisfactory. But we need to do the research now before we can go to the products. And the timeline is depending on the frequency and depending on the problem, 10 to 20 years. So for the slim, I would say that, yeah, this reflective amplifier is a nice thing. We are working on that. And it's the nastiest animal I've ever seen so far in my design life. It's very good research, but don't think you have it yet. I'm going to cause you quite some surprises. So entropy tends to always increase from business to technology. We need to take all out of the existing and make it better. We need to still create something that is not obvious. So from that point of view, it's very nice that we are having these ideas, what we can use, how we can look. Try to make RF to look ideal. We try to do that. We have always tried to do that. Make it in a black box that you don't have to care. 2G in GSM, we needed to go and optimize the system against it. Now, maybe this is too much to ask also this time for the 6G. So better to understand better what we can do before we go. Thank you very much.
Arno, we can take a few very short questions to keep time and let you time also to go for coffee. So please. No one? Ah, there.
Thank you very much for that talk. I'm a big believer in being real when it comes to hardware. Let me ask a question. How many of you have actually used 5G millimeter wave on a phone? One person? How do you know that? Well, that's what I'm asking. How would you know that, right? Right. No. So we have done a lot of research and measurements on actual 5G millimeter wave base stations in the US where we've connected with a phone. The thing that was never, I think, taken into account was is your phone capable of receiving 2 gigabits per second without heating up over 30 seconds? So when we found that and we wrote a paper, my student did thermal imaging with an infrared camera to see where the hotspots are. It's where the antenna elements are. And we presented it at a conference. After the presentation, people from AT&T, from Verizon came up to me and said, yeah, we kind of realized that very soon, but they don't talk about it. So I would encourage people in academia to be a little bit more challenging about assumptions about what you can do at these very high frequencies. I think millimeter wave has a lot of promise, but probably not to your phone. Let's find the right application for using these high frequencies, and let's not try to think we're going to run around with phones doing terahertz, but try to find the right application. Great presentation. So more a comment than a question.
Yeah. I kind of agree with that. And the other story, when I went to industry, and that was by the time of the 3G, I was hired to reduce the energy consumption of current 3G system because it was taking too much. And if you are giving up in the first trial, that's also not the right way to go. So we have a lot of time to optimize, but I also agree with you very much that there is a lot of things to be done. And I'm kind of surprised that for us hardware engineers, we have been requested to do the things what we are asking. I was asking the first time to make a terabit at terahertz. I say that I can try 100 gigabit at 300 gigahertz and to see if that is feasible. So don't even try farther than that. And I know that there is this long path towards the real things with that. And we've seen it in the millimeter waves, and we need to move forward. We shouldn't give up because otherwise you're never getting it. When your spectrum is ending, you're already filling it completely up at lower frequencies. So this is kind of a hen and an egg problem, and that requires engineering effort and a lot of it.
Okay, I think we can conclude here. So let's give applause for Arno and rest of the talks today.